I wanted to find the velocity of this wave continue. What would I do to get that? I'm going to integrate that. And so this is a of t too, except it's all constant. Acceleration is constant. No t terms in it. It's leaving out drag. So if I were to want to integrate this, what do? I mean, so I have cosine f integral potentially. I have cosine of 330, so integral has like sine of this, then negative cosine. Am I doing this right?
No. Thinking about your expression as I go for now.
So here's the thing. All that stuff that I was just saying, the integral of this, derivative. The integral of this, if this was cosine of x or cosine of t or whatever we're integrating with respect to, then yeah, it'd be sine. Alright? I mean, the integral, what I'm saying here, the integral of cosine x dx equals sine x plus some constant. Okay? But I don't have my variable in here. Cosine of 330 degrees is a constant. And so is 116 meters per second, and so is everything else here. I don't have a single t in this whole guy. Alright? So what I'm essentially asking you is what's the integral of 2 or c, some generic constant. So what is the integral of c? If I want to just integrate c dx.
The c falls away.
No,
that's
you
derivative
pull the c out.
going up.
Oh.
You pull the c out and then you drop it and add out.
So this just equals cx plus again another c. C the second. Okay? So all of this, like I said, and so I'm going to be calling this stuff, which is a technical term, from here on out, because I don't want to rewrite it. All of this stuff here, is constant. Alright? There's not a single t in that. That's what we're integrating with respect to. So the integral of that is simply stuff t plus a constant. So what's my constant going to be? So this is going to be v naught. That's my constant. So what is v naught?
134 meters per second.
Yeah? So it's a vector though. So vectors have magnitude and direction. Okay? So yeah, I mean, Adam's right. This comes into it. Yeah, so it's going to be again multiplied by, it's going in the same direction. So my v naught is going to be the 134 meters per second, once again, times going the same direction, cosine of 330 degrees I plus sine of 330 degrees J. That's my v naught. That's how fast the plane was going, the direction the plane was going when we started this off.
And then you can add
Yeah, so if I wanted to actually say, like, okay, after 3 seconds, or whatever, how fast is my velocity? Yeah, I'd take my 3 seconds, multiply it through here, so basically 3 seconds times this, and then I'd add it on to this, and that would be the answer. That's how fast it's going after 3 seconds. Is this making sense to everybody? And so, if I wanted to go around again, position out of this. said, if I wanted to know the velocity at 3 seconds, I would drop the 3 into here and evaluate that. Is that true? Given an assumption I made at the beginning, this kind of assumption here, where I said the rocket motor burns for 2 seconds.
If it only burns for 2 seconds and it gets up to speed in 2 seconds, then is it going to be slowing down the remainder of the way? It's not
That'd
gonna
be drag. We're ignoring drag. Yes, with drag it would, but we're going to ignore drag.
Okay, so is T at that point a constant?
So what happens is your acceleration after 2 seconds goes to 0. So the graph, so acceleration, the magnitude of acceleration with respect to time, it's going to go up, and we're going to ignore the gravity component for the moment, it's sort of a minor component. We'll focus on the rocket motor part of it. So acceleration is going to go, it's constant for 2 seconds, and then it's going to drop to 0. So this is T down here, this is 0, this is 2 seconds. So that's our rocket motor burn. Okay? And after 2 seconds, the rocket motor is done. So our acceleration goes away. And so now V, again the magnitude of V, V here, and this is again split Z. So the acceleration is the slope of the velocity, it's the derivative of the velocity, derivative of the slope. So it's constant. A here is constant, which means we have a constant slope for our V. The y-intercept is the V naught. So we're going to start right here. This is V naught. Okay? We're going to go up with a constant slope. So our 2 seconds is still 2 seconds. And then our velocity is going to be constant. We're ignoring drag. And we're ignoring gravity. Gravity really becomes full right speed. So there we get this. Now our position, we want to keep this thing going. So now we need to essentially graphically, so to speak, integrate this guy. So our y-intercept is going to be P naught. So I'm going to say that's right here. P naught. And we're going to take off. So our slope is initially this. This velocity is the derivative of the position, which means it is the slope of the position plot. So we're not starting with a 0 derivative, we're starting with V naught as our derivative. So we're starting off like this. So it's not going to be coming off like that or anything. It's coming off already with a certain quantity of slope to it, that quantity being the V naught right here. So it's going to start off, say, going that way, and we have it right here. It's basically an x squared or a t squared type function. So normally we have, say, x squared goes up like that, right? Pretty much x squared. And so this is that plus this. So basically adding these together. So this is going to go up even faster. And then when it gets to t equals 2, this part of it's going to drop off. The slope's not going to be increasing anymore. The slope is going to become constant, which is to say a straight line. So then we're going to continue in a straight line. So for this part, from t0 to t2, the slope is increasing, because our derivative right here is increasing. Then at that point, the t2 spot, the slope is not increasing anymore, the slope becomes constant, this is now a straight line. So if you wanted to actually integrate this at 3 seconds, this is sort of a non-continuous function, so you'd have to sort of do it in chunks. You'd have to say, okay, I can integrate from here to here just fine, alright, with this function. And then, so all of this is, all of these functions, these are just from 0 to 2. These are for t from 0 to 2. Just things change after 2 seconds. They change in this way. Acceleration drops to 0, velocity becomes constant, and position starts going up at a linear rate at t2. This is kind of a special case one. But I want you to know where they exist. They exist all over the place in the real world. You follow what I'm doing here? And for me, doing this sort of graphically like this is helpful in kind of understanding what is going on. I feel like I'm having some blank faces here. Is that correct, or is there some level of understanding?
I guess I've never plotted them before. You know what I
Plot of
mean?
the derivatives?
Right.
Really?
I think you,
What are you doing in math class?
so before you time it was, you have a week, infinity, something.
So if you just time, say to this guy, if you just plot 3 seconds into this equation, you will not have the right answer. That would be as if the rocket motor was still burning all the way through 3 seconds.
That's only good up until 2 seconds.
Yes, that's what I'm saying. All of these equations are only good between t equals 0 and t equals 2. Okay? They're only good in those areas. So what you would do, let's say you wanted to know the position. Alright? You can plug 2 into this and it works just fine. You get a number. That's how far it's gone after 2 seconds. Then, you're going to use this velocity you got up to. Again, you plug the 2 into here, you have some velocity, whatever it is. And you multiply that by however, say you want it to go to 5 seconds. You want it to know the position after 5 seconds. Okay? You're going to plug the first 2 seconds before it goes into this, just fine. You get a number. The remaining 3 seconds, it's going along at this velocity. Position, velocity times time. Right? So you find this velocity, which you get by evaluating this guy at 2 seconds, because it's not changing after 2 seconds. Multiply that